Hello, I'm Tony Velasco, and I'm accompanied by Ornin Akarians, David Struns, and Jesus Sanchez. For our ME157 capstone project, we decided to design an automated motorcycle lifting mechanism. In this presentation, Jesus will cover the QFD created for the lift design, Ornin will go over graphical synthesis, mechanism motion, and kinematic deliberation of the project. I will go over the force analysis the team conducted on the lift, and David will go in depth on the simulation the team ran on the design. The motivation for choosing this project stems from the following videos. As seen in those videos, motorcycle users tend to have an issue when attempting to load their motorcycle onto the bed of their trucks. After conducting research, there were no lifts that have been designed with motorcycles clearly in mind. The design team decided to remedy this by creating a winch-powered lift that had a longitudinal ramp for easy loading and unloading. This stands in stark contrast to current designs that require the user to place their motorcycle perpendicular to the bed of their truck, resulting in the offloading process being quite challenging. The design developed would overcome this obstacle that many current motorcycle owners face. In addition, our ramp's large loading platform of 6 feet by 2 feet ensures versatility no matter what has to be loaded onto an average-sized truck. The team's objective with this capstone project was to design an electric lift that would load a motorcycle up to a weight of 300 pounds into a standard mid-sized truck. The goal is also to analyze the design lift to verify the safety factor of all critical components, ensuring a well-functioned and safe design for the eventual customer.
For this slide, I will be discussing the quality function deployment of the lift design. For the 8-step process of the QFD, the who is the end customer or lift customer in our scenario or case. What is based on the customer or client requirements shown on the left column by ease of use, safety, lifting operation, compact, lightweight, and battery powered. For the who versus what, a fixed sum method was used to score and identify what are the most important requirements of the customer to optimize for the lift being designed. The now column shown on the right evaluates the competitor's product of the Caton lift and Pitbull lift with our design, and they are being scored out of 1 and 5, 1 being very bad and 5 being very good. Going down the columns, our design created was scored to be better than the competitors based on the judgment of the competitors' lifts in use. The how section quantifies the requirements shown in the what column on the left through dimensions in meters, durations in seconds, displacement in meters, mass in kilograms, charge in coulombs, and load lifting force in newtons. The what versus how scores the relationship depending on how important they are dependent on the method that is being quantified. How much takes the summation of the what versus how and is used to divide the column sum by the total sum, estimating the score of the lift being designed. The how versus how section identifies correlation based on the other how quantitative characteristics to state high correlation, slight correlation, or no correlation.
In order to obtain the correct orientation of the 4-bar mechanism, we use the graphical synthesis method as it is displayed. To find the location of the pivot points of the linkages, we hand sketch the graphical synthesis and used our knowledge and skills we learned in ME154 to establish the correct orientation. Then we use SOLIDWORKS to perform kinematic deliberations to generate a more accurate presentation of the 4-bar mechanism. In order to ensure realistic sizing of the lifting mechanism, the graphical synthesis performed in SOLIDWORKS was designed with consideration of the actual measurements that would be used to build a prototype. This animation of the basic motion of a 4-bar mechanism gave us a better understanding of how to design our lift. Our design includes 6 linkages that are made of 4130 steel alloy square tubings. The links are designed to be in pairs. The 3 links on top are slightly longer than the 3 links at the bottom. The top linkages are 26 inches long and the bottom ones are 23 inches long. These linkages are connected from the lifting platform to the designated pivot points that were determined by using graphical synthesis. I would also like to add that we will be using a winch to power the lift. This winch that we will be using is a Bulldog trailer winch that is rated for 3,400 pounds. The winch comes with the connection box that will be connected to the truck's trailer connector and will be operated by a wired remote controller.
Force analysis for this design was conducted to find the reaction forces of the linkages to ensure proper sizing. The free body diagram displayed on this slide shows the reaction forces F1 and F2 that were to be solved, representing the forces that the linkages themselves had to endure. As can be seen, the force applied to the ramp is 1,000 pounds, representing an automatic safety factor of 2 due to the force that we were expecting the ramp to handle being only 500 pounds. The force analysis of the linkages was completed for 4 different positions to enable the determination at what orientation of the ramp the linkages would be experiencing the maximum amount of force. You can see the calculations that were done based on the free body diagram, and table 3 shows the reaction forces for the 4 different positions and whether they place the linkages themselves into tension or compression. These reaction forces were found at the pin locations on the design and had to be conducted under static conditions. Assumptions for these calculations included a uniform load distribution across the lift platform and negligible torsion load. A similar process was conducted to find the correct winch size for our design. To select the correct size for the winch, a bar was positioned as a placeholder in SOLIDWORKS simulation. The bar has multiple probes attached to it as shown in Figure 3 and Figure 4. This placeholder was then used to evaluate the forces that will eventually be placed on the winch by dividing the stress by the cross-sectional area. A distributed force of 1,000 pounds was placed on top of the ramp. The force calculations for the ramp were done in its lowered and topmost position in order to get a clear understanding of when the winch would have to endure the maximum amount of force. Using SOLIDWORKS, the probes were placed across the cross-sectional area of the steel bar, which computed the average stress that would be exerted on the winch. Then, the average stress was divided by the cross-sectional area, concluding forces exerted on the winch for both positions. Based on these calculations, the maximum force of 1,086.4 pounds was determined.
Hi, I'll be covering the simulations for the motorcycle lift that was designed for this class. We decided that we were going to take apart the assembly and do the analysis for each of the parts individually, since this would give us more discretion with the types of boundary conditions and mesh settings that we wanted to apply, ensuring the best possible results for the simulation. In addition, this methodology had the advantage of localizing an error if a boundary condition was selected wrong. If we had run only one simulation for the whole assembly, the possibility existed that one wrong boundary condition would invalidate the whole simulation. The most critical part are the boundary conditions, since if the problem is not set up correctly, in the initial stage, answers won't be able to solve the simulation correctly due to the inaccurate input data. For the locations where the part we're going to be interacting with the pins, we decided to use the bare load boundary condition, since this would distribute the forces applied by the pin evenly over the whole surface area of the hole. The part that we're going to be welded, we decided to represent through the use of fixed support boundary conditions. While this would not give us a perfect replica of the type of stresses the welds would have to endure, it provided a pretty good approximation of them and a good starting point. We also utilized the distributed force boundary condition for regions where forces were being applied, such as the ramp on which the motorcycle would be placed. For the mesh, we adjusted mainly 4 different settings. We set the mesh resolution to 7, which was the smallest element size that could be selected without applying any of the other tools. And the span angle center was set to 5 to increase the resolution of the mesh in the regions around features that are round in nature. In places where further refinement of the mesh was required, we also used the refinement tool, with it being set to 1. Lastly, for the most critical of parts, we also used the convergence tool. This was enabled for the von Mises stress and set to 5%. This would result in the mesh being iteratively refined until the current simulation result had less than a 5% difference with that of the previous iteration, ensuring the best possible results. Based on this, the simulation indicated that the part with the smallest safety factor were going to be the walls that were holding the ramp in place. The maximum stress was determined to be 9,660 psi, while the filler rod that we are planning on using had a yield strength of only 40,000 psi, resulting in a safety factor of 4.14. Based on these results, the motorcycle lift that we designed is safe to be used as long as the specified weight is kept in mind.
That concludes our presentation for ME157 capstone project. Thank you.